Hey everybody, and welcome to a video on probability theory as scientific inductive logic. This will be the last lecture for our course on inductive logic. So I want to start by reviewing what we've done in this course. So recall that inductive logic is concerned with assessing arguments according to their inductive strength. That is, we want to take an argument and we want our inductive logic to help us to determine its inductive probability. That is, how likely its conclusion is given the truth of its premises. Supposing its premises to be true, how probable is it that the conclusion is true as well? We wanted to construct an inductive logic that was scientific in the sense that it would accord well with common sense and scientific practice. Now, we learned early on, back in week 2, that justifying and constructing such a logic would be no easy task, given the difficulties posed by Hume's old problem of induction, which we also called the traditional problem of induction, which said it would be impossible to rationally justify any system of inductive logic, and also given Nelson Goodman's new problem of induction, what's also called the new riddle of induction, or the Grew paradox, which suggested that some simple ways of constructing our scientific inductive logic would not work, right? Would not be plausible ways to go. So these worries led us to wonder about the merits of pursuing the path we had set for ourselves in week 1, the path of constructing a scientific inductive logic. Perhaps we could take a suggestion from Hume and just rely on our gut intuitions and psychological habits in assessing the inductive merits of arguments. So no scientific inductive logic needed, was the thought. But I wanted to convince us that this was not a good thought. Right? So to convince ourselves of the need for at least some sort of rigorous scientific inductive logic, we looked in week 3 at some of the ways in which our naive assessments of probability can be demonstrably incoherent. Right? So you could think here of the conjunction fallacy as a particular clear example. Or later on, right, our common intuitions about the answer to the Monty Hall problem, which we also get wrong in a demonstrably incoherent way. So this led us to explore the body of research produced over the past 50 or so years by psychologists and behavioral economists exploring common cognitive biases that we exhibit as humans. Having then convinced ourselves, hopefully, that we need more guidance than that afforded by just our naive gut judgments, right? We look to the field of forecasting in week 4 as an initial guide to correcting for some of our cognitive biases and improving the quality of our inductive judgments. The super forecasters that were studied by Phil Tetlock and others supplied us with a toolkit of informal principles and rules of thumb to employ when we're making inductive inferences, right? Things like highlighting base rates or thinking about problems like foxes, right? That is, from different angles, taking on different perspectives or viewpoints. And also measuring the accuracies of our predictions rigorously, right? To hold ourselves accountable and to improve over time. Some of the ideas, right, or some of the ideas behind these informal rules of thumb are codified more precisely in the mathematics of probability theory. So in week 5, we began studying mathematical probability theory as a candidate for serving as scientific inductive logic. And recall that we saw that probability theory is axiomatic, right? It starts with only a few simple assumptions from which we can then derive a number of significant results, most notably Bayes' theorem, which we used a lot in both homeworks and exams. Our exploration of probability theory continued through weeks 6 and 7, where we looked not only at the mathematics of probability at a time, right? That is, the different axioms and rules that constrain probability and conditional probability functions, but also at a pair of rules for updating probability assessments over time as one takes in new information, right? So we looked at standard conditionalization, where you learn a new proposition for certain as your new evidence, and Jeffrey conditionalization, where that doesn't happen, but you have some learning experience that causes you to spread your probabilities over a particular partition of propositions in a new way. We also explored different interpretations of probability during this segment, right? So we looked at probability as rational degree of belief, right? On this view, what probability is the measure of how confident an agent is, a rational agent is, in a particular proposition being true. We looked at probability as relative frequency, where probability is a measure of the proportion of objects in a reference class that have a particular property. And probability is objective chance. So this is the objective chance of particular physical events occurring, like maybe the chance of a coin landing heads or the chance of some atom. Now, as we saw, there are various interesting interconnections that hold amongst these different interpretations of probability theory, right? Most notably, under the right conditions, rational degrees of belief converge upon objective chances given sufficient information about relative frequencies. Right? We saw this in our videos on convergence. Now, having explored some of the mathematics of probability and examined how probability judgments ought to evolve over time, as by conditionalization and Jeffrey conditionalization, we turned last week to the question of whether we could rationally justify probability theory. Right? Ought rational agents' judgments conform to the probability axioms? Now, while we didn't provide a justification of exactly the sort that David Hume had been looking for, we did explore two powerful arguments in favor of the probability axioms, and hence in favor of the theory as a whole, because the whole theory follows from some of those initial probability assumptions or axioms. And those were Dutch book arguments and accuracy arguments. Recall that Dutch book arguments showed that agents who didn't have judgments or degrees of belief that took on a probabilistic form could end up committing themselves to behavior that would be senseless, right? Taking sets of bets that they would for sure lose no matter how the world ends up, right? And in the case of accuracy arguments, we showed that agents who had credences or degrees of belief that, again, didn't conform to the probability axioms would end up being accuracy dominated by other possible credence functions that they could take on that would be probabilities, right? That is, right, here we're measuring accuracy by the Breyer score, right? So if you have a non-probabilistic credence function, right, no matter what the world ends up being like, your accuracy as measured by the Breyer score will be less than some other probability function when its accuracy is measured by the Breyer score. Okay, now there were significant assumptions that went into those arguments, and they are certainly controversial. But supposing that we grant that those arguments, right, provide at least some strong support to probability theory and the update rules that we've discussed, we can then ask, right, can probability theory rightly serve as a scientific inductive logic that we set out in search of all the way back in week 1, right? And that's what we'll look at a little bit for the rest of the video. Well, recall, right, that we said a scientific inductive logic would have to accord well with common sense and scientific practice. So I want to just explore briefly some of the ways in which probability theory does this. It accords well with scientific practice. So one popular view of how science works that's often associated with the philosopher Karl Popper, and sometimes known as falsificationism, goes something like this, right? It says that scientific practice takes on the following form, right? We formulate a hypothesis, right? We derive some logical consequences of the hypothesis, things that would be true if the hypothesis were true. And these also, right, tend to be things that are empirical, right, things we could test. And then we go out and actually test those consequences. We see, oh, do the consequences of the hypothesis in question hold, right? Do they obtain? And if they don't obtain, then we say that the hypothesis is falsified and we reject it, right? So we're going out, right, trying to falsify hypothesis, trying to find out whether or not these logical consequences of the hypothesis obtain or not. And if they don't obtain, we rule out the hypothesis. If they do obtain, then we say that the hypothesis is corroborated, right? And if we keep repeating this sort of process and we keep corroborating a hypothesis over and over again, then intuitively the hypothesis becomes more likely. Right? So, right, intuitively we tend to think that hypotheses that are better corroborated, right, are more likely to be true. And we can ask, right, can probability theory vindicate this sort of intuition, right? So to see that at least to some extent it can, right, let's let H be the hypothesis that we formulated and that we want to test, right? And we'll let E be a proposition that stands for a logical empirical consequence of H, something we can go out and test, right? Now let's also suppose that the epistemic probability that we assign to H and to E is not extreme. That is, it's between 0 and 1, right? So then we never have to worry about issues like dividing by 0 and such. Now let's consider the following sorts of arguments, right? So we might have an argument from not E to not H. So we go out and we find, E is false, and then we conclude H must be false, right? This is what happens when we falsify a hypothesis or a scientific theory, right? We learn that the consequence of the theory is not true, and then we conclude that the theory itself is not true. In the second argument here, we have, right, just the argument from a tautology to the hypothesis in question. So this is the argument where we really haven't done any testing yet. So we don't know whether E or not E is true, but we're just taking what we have as given, maybe the tautology, and saying and considering the hypothesis under that condition. And then the last argument I have is an argument from E to H, right? We're reasoning from the consequence of H, the consequence of our hypothesis, to the truth of the hypothesis, right? Now, it's really right, from the falsificationist point of view, we should say that the first argument is very strong, right? If E is really a logical consequence of H, and we learn not E, then we should be able to conclude not H, right? This part's just really deductive logic, right? And the last argument, the argument from E to H, should be at least something of an argument, right? It should be a stronger argument than the argument in the middle, right? E should give us some more reason to believe H, right? As H becomes corroborated by E, its likelihood should go up. Right? And we can see that this is what happens if we think of the inductive strength of these arguments in terms of probability theory, right? So we would think of, in the case of the first argument, we would think of its inductive probability as just the conditional probability of the conclusion, not H, given the premise, not E, right? Which has to be 1, given that not E logically entails not H, right? So, right, it was a general consequence of our probability axioms, the probability of any proposition X given Y, when Y logically entails X, has to be equal to 1, right? So that's exactly what we want to have happen. In the second case, right, we have, right, the probability that, or the inductive probability of that argument is just going to be the probability of H given a tautology, but of course we showed that the probability of any proposition given a tautology is just its prior probability, right? And then this, in the last argument, right, the inductive strength of that argument will be measured by the probability of H given E, right? But, right, by Bayes' theorem, that's going to be equal to the probability of E given H times the probability of H, all divided by the probability of E. Now we know that the probability of E given H has to be 1 because H logically entails E, right? E is a logical consequence of H. So then we get that the probability of H given E is just equal to the probability of H divided by the probability of E. Now since the probability of E is non-extreme, right, it's a number between 0 and 1, we know that this is going to amplify the probability of H, right? That is, the probability of H given E is going to be greater than the probability of H because we're dividing it by a number between 0 and 1. And in fact, the lower the number is, the less probable E is, right? Which is to say, right, the more surprising that E is as a consequence that we would observe, the higher the probability of H given E is going to be. So this aligns with our sort of common sense intuition that the more a theory is better corroborated by a really surprising prediction rather than a prediction that we already figured would probably happen whether or not the hypothesis in question were true. Right? All right, so then we have, right, the argument at the end there at the right is a stronger argument than the argument in the middle, which is exactly what we wanted, right? As theories get corroborated or hypotheses get corroborated, their probability goes up. Now we also commonly think that more evidence, right, tends to support a hypothesis better than less evidence, and that more varied evidence tends to support a hypothesis better than relatively homogeneous evidence, right? So let's see if at least some of this intuition can be vindicated in the context of probability theory. So let's consider an example. So suppose that H is the hypothesis that a drug X never causes liver damage, right? And we'll let E1 be the proposition that X doesn't cause liver damage in person 1. And we'll let E1000 be the proposition that drug X doesn't cause damage in any of persons 1 through 1000. Right? Now, truly, we could consider, right, two different arguments here: an argument from E1 to H and an argument from E1000 to H. And truly, right, the second argument from E1000 to H is a stronger argument than the first, right? So we want that to be vindicated by probability theory. We want the inductive probability of the second argument to be higher than the inductive probability of the first, right? Well, if we think of the inductive probability of the first argument, right, it's going to be the probability of H given E1, right, by Bayes' theorem, right? That's the probability of E1 given H times the probability of H all over the probability of E1. Now we know that H entails E1, right? If the drug never causes liver damage, it's not going to cause it for person 1. So the probability of E1 given H is just 1, So we have the probability of H given E1 is equal to the probability of H divided by the probability of E1. And if we look at the inductive probability of the second argument, right, it would be the probability of H given E1000. And we know that, but we can do Bayes' theorem again. We get that's equal to the probability of E1000 given H times the probability of H all over the probability of E1000. Now here again, right, H entails probability of E1000. So we're going to get that the probability of H given E1000 is just equal to the probability of H over the probability of E1000. Now we know that the probability of E1000 has to be less than the probability of E1, right? Because E1000 entails E1. So by our monotonicity requirement, which was a consequence of the probability axioms, we know that the probability of E1000 is going to be less than the probability of E1. But that means in this second case, we're dividing by a smaller number than we are in the first case. So we're going to get that the inductive probability of the second argument is greater than that of the first argument, which is exactly what we would want. Indeed. All right. So then we've seen, right, that at least some very basic ideas about scientific inference find vindication in the setting of probability theory. Right? Has probability theory then given us everything we might have initially hoped for out of a scientific inductive logic? Well, I think not quite, right? So let's consider an example, right? So consider this argument, right? 85% of patients that have taken drug X have recovered. Conclusion, the next patient to take drug X will recover, right? Now, probability theory won't actually by itself tell us what the inductive probability of this argument is, right? Which is what we want of an inductive logic, right? Or full scientific inductive logic, right? It won't do, for example, what Rule S did back when we talked about Rule S, where Rule S would just take this argument and assign it an inductive probability of 0.85. Probability theory won't do that for it. But, right, it will at least do something, right? It does place some constraints on how we go about assigning this argument an inductive probability, right? For example, right, if I take the drug to have some chance of inducing recovery in a patient, and I take this chance to be uniform across patients, and then if I have some initial epistemic probabilities regarding how likely I think the chance of the drug leading to recovery are, right? Then I'm constrained to assign a particular inductive probability to this argument, right? So by making probability judgments for other propositions, I get constrained in what inductive probabilities I can assign to particular arguments, right, by probability theory. So then probability theory doesn't specify unique inductive probabilities for specific arguments because it doesn't tell us what our prior epistemic probabilities should be, right? We could put this as a slogan form, maybe as no probabilities in, no probabilities out, right? So probability theory doesn't just take any argument and automatically assign it an inductive probability, right? That would be asking arguably too much of it, right? But, right, if we have some prior probabilities, which we often do, right? We have some levels of confidence in different propositions. We have some judgments about how likely different things are to be the case. Then probability theory can help us to be coherent, right? And it can indeed act as a powerful guide that directs us in measuring the inductive strength of arguments. Okay, so I think it's fair then to say that probability theory has given us a sort of partial inductive logic, right? Or partial scientific inductive logic. It hasn't given us everything that you might hope for out of a scientific inductive logic, but it has given us something that can help us to be coherent and to navigate the world, and given certain judgments about what inductive probabilities are, come up with further judgments of inductive probability. All right, well, that concludes this lecture. Please remember to complete the participation poll for it. And on Wednesday, we're not going to do another lecture. Instead, we're going to do review for the exam. So I will hold extra office hours, and I'll post this in an announcement. I'll hold extra office hours on Wednesday so we can review for the final exam, which will be on Friday. Please let me know if you have any questions, as always, or feel free to reach out to me or your TAs. Thanks so much for watching, for being an awesome class, and I'll see you guys on Wednesday, hopefully. All right, thanks.